Hello everyone, my name is Saba. I'm a PhD student in the University of British Columbia in Canada. I'll be presenting our work on hybrid DOM-sensitive change impact analysis for JavaScript. This is a part of my PhD work with my supervisors Ali Mesbah and Karthik Pattabiraman. To remain useful, software has to change. Software has to undergo several changes to adapt to the changing environment. Change impact analysis tries to identify parts of the program that are potentially impacted by the change. There's a lot of great research in the area. It has been a popular trend in the community, but most of the work targets more traditional languages. So here, we are here to discuss impact analysis for JavaScript. Most of the challenges in JavaScript analysis arise from the fact that there are different parties playing different roles in JavaScript applications. There's a JavaScript code. There's the document object model, or the DOM, which is a structural representation of the document on the client side, and provides interfaces for modifying and accessing the style, the structure, and the content of the page on the client side. And then there's a server. JavaScript continually interacts with the DOM. DOM is a highly dynamic entity in the applications, and JavaScript functions read and write and modify DOM elements on the fly. DOM is originally downloaded from the server. After that, it takes its own identity and is very dynamic. JavaScript also interacts with the server constantly throughout its execution. XML HTTP requests, or as we call them, XHRs, are used to send messages to the server and receive responses. So all these different parties and their interactions introduce new types of relations that are often easy to miss in the applications because they're implicit, they're hidden somewhere in the application, but they can transfer the impact through new means in the applications. We're going to discuss some of these challenges here with examples. The first challenge is that the impact can get transferred through the DOM between two JavaScript functions, even though there's no relation between those functions in the code. If you look into this example, the function gets all the instances of a certain class and modifies their textual information. In this example, this element's value gets modified because it matches the criteria. Another JavaScript function that can be in another file is not necessarily co-located with this function. Later, reads a DOM element based on its ID and uses its value to make a decision or take some actions. In this example, there is one element that matches both criteria. So this div element fits the first criteria for the class type and also is retrieved with the second function. But there's no indication in the code that these two DOM elements are actually the same. But during the runtime, we can figure out that these are actually the same DOM element. So the same DOM element was written by the first function, was later read and used by another function. And this makes those two functions be connected, even there's no relation between them in the code. And this is how the impact can transfer from the first function to the second through the DOM. A similar concept is valid for the event mechanism of JavaScript. JavaScript is an event-driven language. There's usually the case where DOM elements are assigned event handlers, and when an event is triggered on the DOM element, the handler is called. In this example, the handler is assigned to one of the elements, so when it's clicked, the handler gets called. But there's this notion of event propagation in modern browsers. A single event can propagate on the DOM tree and call multiple handlers of the ancestors of the target element if they have the handler for the same event. So here, the parent of the target element, has a handler for the same event, which is a click. So when the user clicks the div element, first the event handler of the target element is called, then the event propagates on the DOM tree and calls another handler indirectly. So one single event can trigger multiple handlers in the DOM tree without those handlers being directly assigned to that DOM element. So this is another type of hidden relation that is really easy to miss in today's large-scale applications. The final category of challenges that I'm going to address here are the challenges that arise because of the interaction of JavaScript applications on the client side with the server. JavaScript applications use XHR messages to send messages to the server. When this response comes back from the server, the browser calls a callback function that was identified by the XHR message. But it's not always obvious how these relations work. In this example, an XHR is being created by the function, but the callback function is evaluated dynamically through concatenation of an action that gets retrieved from the user plus a string. So there is no way to know statically what the callback function is. It's during the runtime that we can find out what function gets executed, what data was sent to the server, which will affect the behavior of the server, which will change probably the response that comes back from the server and is used throughout the application. So all these relations, if I want to summarize the challenges, all these are implicit relations that exist in the application, but are very easy to miss because they are not trivial to find and they're implicit in the code. And in addition to all of this, JavaScript itself is a highly dynamic language. That makes analysis of any sort of JavaScript application more difficult. This was sort of our motivation for doing this research. But do these assumptions actually happen in the real world? Some of them we already know that they do. XHR messages are used all the time. Dynamism of JavaScript has been investigated a lot in the community. But the parts that we wanted to investigate were the DOM-related and event-based interactions. Do these actually happen in the real-world application? Is there a case where a DOM element is written to a JavaScript function and read by another JavaScript function and can transfer the impact? So to find this out, we conducted a small exploratory study. We got 10 web applications from GitHub trending applications, JavaScript contests, and so on, and we analyzed them. We gathered some data about the interactions between JavaScript and the DOM, and also the events that happened and propagated on the DOM tree. We further analyzed some of the structural characteristics of the graphs. I'll get back to that later. The results of our study showed that 42% of the DOM elements that were involved in the analysis could potentially serve as media for transferring the impact between JavaScript functions. So this means that a DOM element was written to by a JavaScript function first and read by a JavaScript function later and could transfer data. But there were many-to-many relations. Multiple JavaScript functions were interacting with multiple DOM elements, and this could go on for several levels. So the chain would not end by just the second function. This would happen even to 5 and 6 levels in the applications. The results also showed that 14% of the handler that were called by propagation and not directly by a DOM event. So these results show that we need to take into account these DOM-related and dynamic information about JavaScript applications when we are trying to analyze JavaScript applications. To address these issues, we proposed the hybrid analysis. There's a lot of static analysis on JavaScript. We saw the necessity to combine it with dynamic information. And integrating these two types of analysis, we came up with a hybrid model for the application. This hybrid model contains the important entities in the application and the relations that we thought would matter in the analysis, and is basically a graph. So using this graph, the users can query the model and find out the impact sets of the change sets. So for each entity in the application, they can find the set of potentially impacted entities in the application. We also proposed a ranking mechanism to sort the impact set because there could be multiple entities in the impact set and wanted to give users an indication of what matters more. Let's start with the static analysis part. This is pretty straightforward. We start by forming a control and data flow graph of the JavaScript application. JavaScript functions are first-class citizens in the application, so we treated them the same way as we would treat objects and build a model that creates objects and functions. But because because static analysis can be overly conservative, we removed some of the relations, some of the control dependencies if there was no data dependency involved through argument, passing, return values, or global variables, and came up with a modified pruned graph. This is an example of what the static model looks like so far. So there are functions that can be detected statically. Not all functions can be detected statically in JavaScript functions, in JavaScript applications. There's no notion of the DOM elements yet because they have not been created. They're completely dynamic. But there is a hint of XHRs because you can usually find out when they're created, when they're sent, but there's no information about the data that is being sent or maybe the response that comes back. So it's still missing a lot of parts. That is when we move on to the dynamic part, and we try to augment that model with the dynamic information. Sort of the dynamic information that we collect at this stage start with the interactions with the DOM. We collect all of the accesses that are made to the DOM, the direction of the flow of the data, the type of the access, and we form the dependencies that can mean impact transfer through the DOM elements. We also collect the information about the events, whether they were propagated, whether they were normal events, the data that is being passed, the involving elements and functions, and the same for XHR relations. XHRs go through different phases during their lifestyle. They can get created, sent, and have their callback at different places. So we collect all of those information and we make the connections in the graph. And we add the dynamic call graph, of course. This is a little bit different than the static call graph because of the dynamism of JavaScript. To give you just a couple of examples of how dynamic JavaScript is, through eval, functions, JavaScript code can get executed and created dynamically. You can have functions getting created dynamically that they're just strings or were concatenated or just created on the fly. But here, if they interact with other parts of our model, if they access a DOM, if they send a request, or if they're assigned as a callback, then we capture those functions and the relations that they have with the rest of the model. To give you another example of the dynamism of JavaScript, JavaScript function calls are not necessarily faithful to the function signature in terms of the number of the arguments that they can use. So you can use any number of arguments, and JavaScript is loosely typed. So in order to get a more precise sense of the data flow in the application, we needed to take into account all those dynamic features in our call graph. This is an example of the output of the dynamic phase. You would have a dynamic model. Here you have some functions. You have a couple of functions that were not detected statically. You may have functions that were detected statically but were not invoked dynamically, so they're not shown here. But you have the DOM elements and how they interact with other entities in the application. And you have more elaborate relations for the XHRs. If you have the responses as they happened, and you have all sorts of, and you have the exact data that was used during the runtime. So this brings us to our hybrid model. We have the static analysis, we have the results of the dynamic analysis, and now we can create a hybrid model of the application, putting those two together. So this is, again, a very simple example. We'll show you the core of our hybrid model. Our hybrid model is basically a directed graph. The nodes in the graph are the entities that matter to us. JavaScript functions, DOM elements, XHR objects, those are our entities. These entities are connected through directed and labeled edges. The direction of the edges show the direction of the data flow. The labels show the type of the accesses that were made that are different between different sort of entities in the model. So in this example, the gray nodes show the nodes that come from the static analysis. The green nodes show the nodes that come from dynamic analysis. The gray nodes with green borders show the entities that were common in both types of analyses. Okay, so having this model, we can traverse this graph and get the impact set of each change set. In this example, if you start from each of these nodes, for example, the calculate tax node, and follow those links, traverse the graph forward, we can get the impact set of the function, which are the potentially impacted entities by that function. But as you can see in this example, calculate tax almost interacts with everything else in the model, all other entity. You can reach almost any other entity from this function. This will tell us that there are cases where the impact sets can get very large. Because we have static analysis involved, there is over-conservativeness in our approach as well. So we had to come up with a way to show users what is more important in this impact set. We wanted to sort these impact sets. So we came up with our own set of impact metrics, as we call them. Most of these metrics came from our earlier study where we investigated the structure of the graphs, and we investigated the correlations of topological aspects of the graphs with the dynamism of the graph and how the impact would transfer. So the first 4 metrics come from our study. They had hard correlations with the amount of DOM sensitivity and dynamism of our graphs. The last 2 metrics are kind of are based on our intuition. The first one is the distance, the minimum distance of the investigated element from the change set, because we thought the closer the entity is to the change set, the more important it is to the developer. If they're changing an area, then they will care more about the closer entities to that area. And also we made this a recursive function. So if all of the entities that impact this element have higher impact, then that would mean that that entity could be of higher importance. So we use these impact metrics to sort our impact set and present a sorted set a rank set to the users. We implemented our approach in a tool called Tochal. It's open source, available on GitHub, and you're welcome to use it, extend it, and let us know what you think. To evaluate our approach, first we wanted to compare our analysis with static analysis and dynamic analysis alone, because there is no quite similar approach for JavaScript. So we decided to compare with static and dynamic analysis in terms of the completeness of our analysis. We took the same applications from our earlier study. We picked 3 random functions from each application, and we retrieved the impact sets for each of the functions. We compared the size of the impact sets between these applications for each method, because the impact sets are dependent on the change sets that you pick. So we wanted to have an overview of how the analyses were working. So we compared the dependency graphs of each application as well for each method. The results of comparing the impact sets showed that static analysis covered 26% of the entities in the impact sets of the hybrid analysis. And dynamic analysis was able to find 80% of the impact sets of our hybrid approach in average. Then we compared the dependency graphs and not just the change set, just the impact sets. So comparing the sizes of the model graphs showed us that static analysis formed 59% of the hybrid graph. Dynamic analysis formed 84% of the call graph, of the hybrid graph. But there was part of the graph that was common between static analysis and dynamic analysis. So next, we wanted to know what parts come exclusively from static analysis, which parts came exclusively from dynamic analysis. And we set aside the common parts between the two. So 15% of the dependency graph came from static analysis alone, and 42% of the graph came from dynamic analysis exclusively. So this shows us the necessity of a hybrid analysis. There are parts of the analysis that are detected by static analysis, are not invoked dynamically. We don't capture them at runtime. And because of the dynamism of JavaScript, there's a large part that cannot be detected statically. So we do need a hybrid approach for a better analysis of JavaScript applications. As a last step, we wanted to know how our approach will perform in real-world settings. We wanted to see how it will help real developers perform analysis tasks in real settings. So we designed a user experiment. We recruited 12 participants from a large software company in Vancouver. We gave them 4 analysis tasks. And then we wanted to measure their performance. We had to quantify performance. So we measured the time of completing each task and also the accuracy in which they responded to the task. The results of duration showed that for all of the tasks, using Total improved the task completion duration, and the results were statistically significant in total. We observed an 80% improvement in the time in which the developers finished the task. We also compared the results of the accuracy. Again, we see a significant improvement for all of the tasks in terms of how accurate they were able to answer the questions. And in total, we saw that the users of Total were 2 times more accurate in responding to the questions. As a final step, we also wanted to evaluate our ranking mechanism. Did our impact metrics and sorting the impacts that help developers in finding what they were looking for? So we designed 2 tasks very similar to each other. 2 of the tasks required approximately the same level of effort, the same sort of thought process to finish, but we turned off the ranking mechanism for one of them. So 2 similar tasks, one had the ranked results, one results were just randomly ordered. The results of comparing the duration showed that having the ranking mechanism helped users be 2 to 3 times more faster than the control group. The results of the accuracy were very close. We still saw a 25% more accuracy, but this makes sense because the impact sets were already there. The users were able to find the answers if they put the time, but it would just take them a lot more time to find the correct answers. To conclude my talk, I briefly mentioned a few of the challenges that are involved in analyzing JavaScript. There are a lot more. We conducted an exploratory study to find out if they actually do happen in real-world applications. We proposed a hybrid of static and dynamic analyses that take into account the features specific to JavaScript and how it interacts with the DOM and the server and so on. And the results showed that our approach is able to help real developers perform their everyday tasks faster and more accurately. Thank you for listening. With that, I want to conclude my talk.
Okay, we do have time for questions and general discussion.
Thank you for your talk. My question is about obtaining the dynamic analysis. So how difficult was it to find good enough coverage of the program that your dynamic analysis exposed the amount of the call graph that it did, the amount of the execution that it did?
It is indeed difficult. So either the programs have to have good test suites that have high coverage, or if they didn't, we needed to take like an exploratory testing approach and come up with scenarios to try to cover as much as we could. And then we did this through the multiple executions and combined the results. So it's a similar problem that they have in testing, having high coverage, and it's indeed a problem, but we try to follow their principles.